Hi everyone, my name is Victoria Petley, and we are Team 6 with Mariah, Alex, Asher, and Mohammed. Today I will be presenting our design and implementation of a Polyphase Filter Bank on a Xilinx FPGA for MKID readout systems. Our mentor is Dr. Tracy Jamison Hoods, and we have been working on developing the readout system for the Habitable Worlds Observatory. The Habitable Worlds Observatory, or HWO, is NASA's next flagship mission. It will be the first space telescope specifically engineered to search for and characterize Earth-like exoplanets. The HWO employs MKID detectors because they are among the most sensitive photon detectors available, capable of capturing extremely faint signals from distant worlds. MKIDs are superconducting resonators that behave like LC circuits. Each MKID has a specific resonator frequency, similar to how each guitar string has a natural pitch. In these diagrams, you can see when a photon interacts with an MKID, the resonator frequency shifts slightly, causing a phase change. Capturing these shifts is how we know a photon has been detected.
In our system, each resonator signal can be thought of as a tone, a signal at a single frequency. When a photon hits the detector, it shifts the tone slightly. By monitoring these tones in real time, we can detect individual photons and measure their properties. Let's look at how the signal travels through our system. The detector captures the photon signal, which then passes through an analog front end to prepare it for digitization. Next, it goes into an analog digital converter, an ADC, which digitizes the signal. The digitized data is then transferred onto an FPGA, which handles the processing of the signals. An FPGA, or Field Programmable Gate Array, is ideal for MKID readout because MKIDs produce fast, broadband signals that must be processed in real time. FPGAs can perform massive parallel signal processing, mixing, filtering, channelizing, and tracking thousands of resonators simultaneously with nanosecond timing. This real-time capability is essential. Without it, we wouldn't reliably extract the photon information needed for the science.
Our design process begins right after the data reaches the FPGA. We start by simulating a frequency plane to extract specific tones and determine the necessary resolution and channel spacing for the MKID readout. We then develop a fixed point model of the Polyphase Filter Bank in MATLAB and in Xilinx to simulate and verify the design's performance. Using Xilinx's HDL code generator, we produce Verilog code for FPGA implementation. Currently, we are conducting hardware testing and verification, with the next step being a hand-coded VHDL implementation to meet NASA's rigorous space flight requirements. Now we're going to talk about the theory of the Polyphase Filter Bank and how we designed this project. Before diving into the Polyphase Filter Bank, let's first talk about the digital down converter, or the DDC. This is widely used in radar and astronomy. Sometimes we want to isolate a specific feature or a specific tone within a broad bandwidth. The DDC is a common tool used for doing this. However, this process only extracts a single frequency tone. Our instruments don't observe just one frequency, they observe an entire bandwidth containing many tones. For example, if there are hundreds or thousands of tones within that bandwidth, we would need as many DDCs, hundreds or thousands of DDCs running simultaneously to extract each of those tones. This approach quickly becomes inefficient and exhausts FPGA resources.
As you saw on the slide before, when we combined the filtering and the downsampling, the architecture of the DDC was changed. So now let's look at a traditional filters architecture, which is important to understand before introducing the Polyphase Filter Bank. So a traditional filter consists of a chain of delays and multiplications with the filter coefficients of the impulse response. We then split this filter into multiple subfilters called polyphase components. Each subfilter corresponds to a phase of the original filter and is arranged into rows. This reorganization is the core of the polyphase architecture. For example, if we have a filter of length 16 downsampled by 4, it becomes 4 subfilters of length 4 each representing a phase of the filter. The PFB combines these subfilters with an endpoint FFT. While the mixer in a DDC targets one frequency tone, the FFT extracts many tones simultaneously, one for each frequency bin. This completes the Polyphase Filter Bank architecture, a filter plus an FFT. Now, why do we need a PFB for the MKID readout, and why is it a mission requirement? So MKIDs are multiplexed, meaning thousands of frequency tones are packed closely together. When we perform an FFT, we divide the spectrum into bins. Ideally, each tone would fall exactly into one bin, but because the tones are so densely packed, many fall between bins, causing spectral leakage. Spectral leakage spreads signal power into neighboring frequency bins, blurring the spectral response and making it harder to detect weaker signals, or as you can see here. The PFB solved this by creating subfilters around each FFT bin. These filters catch tones that fall between bins, greatly reducing spectral leakage and ensuring even weak signals can be accurately detected. For the HWO, the PFB uses a 4096 tap low-pass filter with a Blackman-Harris window and 1024 polyphase components. Implementing 1024 rows of the filter directly would be very resource-intensive, however.
To address this, we designed a low-speed polyphase filter bank architecture. Instead of using massive logic resources, we store the filter coefficients in block RAM on the FPGA and stream in each phase sequentially at the clock rate. This approach significantly reduces resource usage while still strictly meeting the HWO mission requirements. Here we can see our hardware implementation results. To verify accuracy, we use the formula n times signal frequency over sampling frequency. This tells us exactly which bin our tone should appear in. Based on our parameters, the formula says our tone should be at bin 480. Looking at the graph, this is exactly what we see. The tone is isolated in bin 480. You can see our start signal on the left and our end signal on the right, which frame the full 1024 channels. You might notice the extra tone on the right. This is simply a mirrored alias tone, which is standard case when passing samples through the ADC. The photo shows our actual setup in the lab. The image on the left screen is the Vivado hardware manager. This is our algorithm results displaying the processed results coming directly from the FPGA in real time, proving the successful physical implementation of the design. In conclusion, verifying this algorithm on hardware is a major milestone. We've proven that our polyphase filter bank is not only functional, but far more efficient than traditional methods, freeing up critical FPGA resources needed for spaceflight. Technology directly empowers Habitable Worlds Observatory. By eliminating spectral leakage, we allow the system to detect faint biosignatures that would otherwise be hidden in real sense. The signal processing we demonstrated today brings us one step closer to discovering new worlds. For us, taking this theoretical model to a working 1024 channel design has been incredibly rewarding. We've gained specialized experience in DSP and FPGA development under the guidance of Dr. Tracy Jameson Hooks, building a strong foundation for our future career.